Okay, so big day today. We're going to do our first hypothesis test. So last time we spent some time talking about how to come up with hypotheses. And then we talked about interpreting our conclusion at the end of a hypothesis test. Today we're going to fill in the information in the middle. Okay? So we are in particular, we're going to do hypothesis tests for claims concerning population means. And similar to how we started with confidence intervals, we're going to start with the assumption that we know the population standard deviation, that we know sigma. In 10.3, we'll get rid of that assumption that we know sigma, and then in 10.4, we'll work with proportions. So same kind of pattern we followed for confidence intervals. Okay. All right, so here's our general outline again. When we're doing one of these hypothesis tests, okay, we have to start by coming up and stating our hypotheses. Okay. Then next we'll figure out what type of distribution to use. Okay, for us, we have two, right, that we use sometimes. We have Z and we have T. Okay, and then we'll state the level of significance. Then we'll calculate our sample statistic, or our test statistics, really, what that should say. And then we'll draw a conclusion. Okay. So these kind of lump into one for us. Mostly when we figure out which distribution to use, that tells us what formula to use, and we can do our calculation. And then we'll use the level of significance to draw a conclusion. Okay, so it's not quite as bad as it seems when you see all that written out. Okay. So to get started on that, we have one little piece of information we need to discuss. Okay. Something we haven't mentioned yet, when we do a hypothesis test, there are really like three types of hypothesis test. They're really similar. Some of the little details are a little different. Okay? But what determines which type of hypothesis test we're doing is which symbol we have in the alternative hypothesis. Okay? So we have three possibilities for a mathematical symbol in our alternative hypothesis. Okay? So each one of those gives us a different type of test we're doing. Okay? So just slightly different. If we have a less than symbol, again, you can think about that as an arrow that points to the left. So that means we're doing a left-tailed test. That's what we'll call that. All that means is we'll be working over on the left side of our distribution curve. Okay. If our alternative hypothesis has a greater than symbol, think about that as an arrow that points to the right, and that means we're doing a right-tailed test. And then the one that's a little weird is if we have a not equal to symbol, that means we're doing a two-tailed test. Okay, so we're going to be dealing with the left and right sides of our curve in that case. Okay. So points to the left, it's left-tailed. Points to the right, it's right-tailed. If we have a not equal to symbol, it's two-tailed test. Okay. So that's another reason why our hypotheses are so important, because the symbol we have in our alternative dictates which one of these we're doing. Okay. Just a second ago, I thought of something else I needed to mention, and I don't remember what it is now. Oh, so hopefully you saw my note I posted on Canvas, okay, about the null hypothesis. Okay, they've changed how they're doing things in this edition of the textbook, and I didn't realize before class. Okay, so in the null hypothesis, Hawks will always want an equal sign in the null hypothesis. Okay, so we're not necessarily thinking about doing the opposite symbol. Okay, the null will always have an equal sign in there. Okay, that is fairly common. Okay, fairly common way to do it. So just be aware of that. nothing changes on coming up with alternative hypothesis. It's just the null. Okay. Questions on the three types? How to tell the difference? Okay. So that's important. Okay, the next thing we need is we need a way to calculate that thing that we were calling a test statistic. Okay? And we need, in order to get there, we need to know which distribution we're using. Okay? So in this situation, okay, let's back all the way up. Okay? In this situation where we are hypothesis testing for a mean, and we know the population standard deviation, okay, then we'll always use the same distribution in here. And we'll always end up with a z test statistic. Okay? Now we got a lot of stuff going on. Okay, it says when the population standard deviation is known, that's the main one for us. Okay. Then we've got the sample's a simple random sample, and either the sample size is at least 30 or the population distribution is approximately normal. That's central limit theorem. Okay. Then we can use this formula to calculate a test statistic. So the good news is we hopefully are familiar with the symbols in our formula now, nothing new. Okay. We got X bar, that is going to be the mean that comes from our sample data. Okay. Mu here, mu stands for population mean. In our formula, it's going to be a little special. We'll come back to that one. Okay. Sigma is our population standard deviation, and little n is our sample size. Sample size. Okay. So I said mu is special. Okay. Mu is the population mean. We don't actually know the population mean. If we did, we would not be doing a hypothesis test. Okay. But the number that we use for mu here is the number that we're assuming to be true as we do a hypothesis test, and that is the number from our null hypothesis. Okay. So whatever our number is in the null hypothesis, that's the number we use for mu. Okay, the sample mean and sample size come from our sample data. And on these, we'll have to be given sigma. So we do that and we get a z-value. We get a z-value. So z-value is just a number on the standard normal distribution, same types of z-values we've been working with. Okay. So nothing too remarkable about that, other than we've got that special situation with mu, comes from the null hypothesis. Nothing else is too tricky there. Okay. Questions on the formula? The reason why we get this weird term in the bottom, okay, and this is, you don't absolutely have to know this, okay, this is kind of behind the scenes stuff. Some of you may be interested. This term is the standard deviation of the sampling distribution of sample means from the central limit theorem section. And that's where this comes from. You don't have to know that. That's where that comes from. So without that part, it looks like the Z formula we've already been using. Okay, there is our formula for test statistic in this scenario. Okay. So we talked about how to do this part. In this section, we're always going to use that Z test statistic, so that's that big of a deal. The level of significance just has to be given to us in the problem. Okay. Gathering data part, that's just going to be given to us in the problem. Okay. We're not going to send out any surveys or anything. And then we've seen our formula to calculate the sample statistic or the test statistic. Okay. So the only piece we're missing And I told you that part would go by kind of quick. The only piece we're missing is drawing a conclusion. How do we take our test statistic and draw a conclusion? How do we decide if we reject or we fail to reject the null hypothesis? Okay. So that's the part that's left. Okay. And there are two main ways that that's done when we do a hypothesis test. In this section, we're just going to focus on one of the two. We're kind of forced into using the other method in the next section, so we'll save it for then. That way it's not quite so confusing trying to learn two methods at the same time. Okay. So in this section, the way we are going to draw a conclusion, and this is probably by far the most popular way to draw a conclusion with a hypothesis test. And the way we're going to draw our conclusion is by using something called a p-value. So our definition tells us a p-value is a probability, and it's the probability of obtaining a sample statistic as extreme or more extreme than the one we got from our data when the null hypothesis is assumed to be true. Okay. So again, think about our situation I kind of mentioned last time. If I make a claim, so I'm making a null hypothesis here that the average age of students at JSU is 80 years old, then what we're doing is we're putting a number on how likely it is to get certain sample values. Okay? So the idea there, if the average age, if we're assuming, okay, starting off assuming the null hypothesis is true, so if we're assuming that the average age of students at JSU is 80 years old, then if the average age in our sample data is 23, okay, then how likely would that be? That's what our p-value is going to tell us. Okay? In that case, it would be very unlikely. Right? That's kind of our intuition on that. You think through that. Okay? But our p-value is going to put a number on there. It's going to put a probability on that. Okay? So we're using p-values to make our conclusions in this section. Okay? So we need to know how to come up with this probability. You didn't realize it, but you've already been figuring out p-values. You just didn't know it. So we're ready. We're ready to calculate some p-values. So let's look at a few situations here. Okay. Let's look at this example. So here we've got some hypotheses for a hypothesis test, and we're assuming part of the work's already been done. Okay, we've already taken the data and put it in our formula and calculated a test statistic. Okay, so this comes out of that new formula that we just saw. So there's our test statistic. And then what we want to do, we want to calculate the p-value for this test statistic given these hypotheses. Okay. So we have two things we have to look at in order to come up with the p-value. The first thing we need to know is what type of hypothesis test are we doing? Is it left-tailed, right-tailed, or two-tailed? So you have to look at the symbol in the alternative hypothesis. Yeah, so less than points to the left. So this is a left-tailed test. Okay. So since it's a left-tailed test, our p-value is going to be the area to the left of our test statistic. If it's right-tailed, we would want the area to the right of that. If it's two-tailed, well, we'll talk about one of those in a second. Okay, so here, left-tailed means our p-value is going to be the area to the left of negative 1.34 on the z-tables. Okay? So why did you make us look up all those areas in the z-table? This is one reason. That's one reason to find p-value. So if we want the area to the left of z-value, we just look it up like it's written. Just look it up like it's written. So if we look up negative 1.34, what area do you find? Got it? Yeah, but I got two. So 0.0901. That is the p-value of our test statistic. 0.0901. Questions on finding that? Again, the way we knew we wanted the area to the left was because we were doing a left-tailed test. Okay? And the z-value we're concerned with is always going to be the test statistic. The test statistic. Okay? Let's look at another one. Okay. These examples I pulled out of the old book stuff. That's why the null hypothesis is not an equal sign, if you notice that. And it doesn't matter for this part, but okay. There's our picture of what we're doing. Finding that area. Okay. So look at this one. Same idea. Okay, we're doing a hypothesis test with these hypotheses. Already taken the data and plugged it into our formula, calculated our test statistic to be 2.78. Now we want the p-value. So we look at our alternative hypothesis. Look at the symbol in there. Is this a left-tailed, right-tailed, or two-tailed test? This one points to the right, so it's right-tailed. Our test statistic is 2.78. So guess what area we want to find our p-value? Yeah, we want the area to the right this time because it's a right-tailed test. We want the area to the right of 2.78. So to find area to the right of a z-value, we can look up the opposite. So our test stat was 2.78, so we could look up negative 2.78. We do that. I got it. Yep, that's what I got too. 0.0027. The p-value in this situation for this test statistic, 0.0027. Mm-hmm.
What you about like this side and null hypothesis being like.
Yeah, so in Hawks, if these are our hypotheses, right, this is the way we talked about doing them last time. So we would come up with this one, and then the way I told you was to use the opposite sign for the null. They're not doing that anymore. Instead of that symbol, they just have equal, always. Yeah, so every null hypothesis you put in Hawks, you want to put an equal sign on the null. Yeah, that's the change. Some people do it that way. It's a little bit lazy to me. Kind of lose some of the meaning that's going on there, but that's okay. It will work. It will work.
And then it with and then null.
Well, the alternative can't ever be equal. The alternative would be the not equal one, right? Because equality always goes with the null hypothesis. Yeah. Okay. Other questions? Yeah, I'm sorry. Yep. Yep. So now every time you do a null hypothesis, it'll have the equal sign. Okay, let's look at one more. We're done left-tailed, we're done right-tailed. We got one other type of test to account for. Now, this one's slightly more effort. Okay. So, doing a hypothesis test with these hypotheses, we take the data and put it into our formula for a test statistic. We get negative 2.15. We want the p-value, so we need to figure out what type of test we're doing here. So we look at the symbol in the alternative hypothesis. On this one, we have the not equal to symbol. So what kind of test is it? Left-tailed, right-tailed, or two-tailed? Yeah, this one's two-tailed. Okay. So two-tailed test, getting the p-value is a little bit more effort because we're not just concerned about the left side or not just concerned about the right side of our curve. We want both sides. Okay, so we're going to have to find the area in two different tails. And the two tails that we're going to deal with, the two z-values that we're going to deal with, are the positive version and the negative version of whatever our test statistic is. Okay, so we're going to take plus or minus on our z-value. So on this one, the tails that we're concerned about, or the z-values we're concerned about, would be negative 2.15 and positive 2.15. So we want the area in both of those tails. So this tail and this tail, two tails. So how can we get the area in both of those tails together? That's it. That's the short way. So, right, because these are opposites and they'll always be opposites on a two-tailed test. And that's why I took time to mention that comes up a lot, because on a two-tailed test, you're always going to have two z-values that are opposites of each other that we're concerned about. Okay. So here, what we're saying is we can look up negative 2.15 to get this area. That's going to be the same as this area. So we just take this answer and multiply it by 2 because it's two-tailed. Two-tailed. So our p-value here, the way I'm going to write it, I'm going to say it's going to be 2 times the area to the left of negative 2.15. Okay. The thing that's a little weird about that is that if our test statistic was positive 2.15, we would still find the p-value the same way. Because if this one was our test statistic, we would want to know still about both of these because it's two-tailed. So we would look up the negative version and then multiply by 2. Okay. So on two-tailed, if you want the p-value, we can just always look up the negative version of the z-value and multiply it by 2. And if you get confused, just make the little sketch. Make the little sketch. How it's two-tailed, so we've got one on both sides. Then that'll help. Okay. So we need the area to the left of negative 2.15. So we look up negative 2.15. And when I get 0.0158, so when we multiply, we'll get our total p-value of 0.0316. Questions on finding p-value? They're really just chapter 6 problems. Just finding an area under the normal curve. Okay. So we only have one little piece of information left, and that we need, then we'll be ready to do a hypothesis test. The only thing we're missing, okay, is what do we do with this number? What do we do with this p-value? How does that help us make a decision at the end of our hypothesis test? Okay. So what we do is we take our p-value and we compare it to whatever level of significance we're using. Okay. And for us, we're always just going to be given a certain level of significance in the problem. Okay. And the level of significance that you use in real life depends on what field you're working in, what circumstances are you in. Okay. In academics, generally, the rule is we'll use a alpha, a significance level of 0.05. If you subtract that from 1, that means we're 95% confident in our result. Okay. So some fields that's good enough, some fields that's not good enough. Okay. So like if you're doing medical research and if you mess up it's going to make people sick, then you might want to be more confident than that. Or if you're just doing something that's not as serious, you can get away with being less confident sometimes. So is the level of significance we use varies, okay, from situation to situation. So we make a comparison between our p-value and our level of significance. The symbol for level of significance is alpha. And so here's our rule. Okay. If our p-value is less than or equal to alpha, or significance level, then we reject the null hypothesis. If our p-value is bigger than alpha, then we fail to reject the null hypothesis. Okay. So it's a simple rule. Okay. The issue there is it's a little tricky to remember when you're first learning. Okay. So let me give you two things. Let me give you kind of the reasoning behind why that's the rule, and then I'll give you a method to use to remember. Okay. Help you remember. So you can think about alpha, our significance level, as being how willing we are to risk making a type 1 error. So type 1 error is when we reject a true null hypothesis. Right? Remember, that's a strong statement, so we don't want to mess up and make a really strong statement that's wrong. So we usually want alpha to be pretty small. Okay? So however willing we are to make a type 1 error, that's usually our significance level. And then our p-value, you can kind of think of, it's not exactly, but you can kind of think of that's the probability of us making a type 1 error based on the data we got. Okay. So if that's small enough, if it's smaller than our acceptable level of making a type 1 error, we reject the null hypothesis. If it's not, if it's too risky, if the p-value is too big, then we fail to reject the null hypothesis. Okay. So that's one way of thinking through that. And then if that doesn't help, this was taught to me by a student from one of their teachers they had in high school. So here's the rule, okay? If p-value is low, so what that's talking about is the first one, right, where the p-value is smaller than alpha. Reject the null hypothesis, but that's not how you read it. It rhymes, right? If the p-value is low, reject the hoe. So, yeah. And it's funny. It makes you remember it, okay? Make sure you remember it. If not, okay, if the p-value is not small enough, then fail to reject the null hypothesis. Okay? So that works pretty well. Okay? Usually will stick in people's memory. So. All right. We're ready. We're ready to do a hypothesis test. Okay. We have a few we're going to go through. So it seems like a lot of steps. but they, after you get a little practice, they kind of flow one step into the next step, so not too bad. Here's one little thing that I left in because I thought was interesting, talking about how we use different significance levels for different fields of study. So here's you're working in particle physics. Okay. It said their standard p-value level for calling something a discovery in particle physics is 0.000003. Okay. So they're serious about it. They're serious about it. Most of the time in academics, and our book says it usually uses 0.05 or 0.01. So this corresponds to 95% confidence and 99% confidence. So this would be what, 99.99997% confident. So it all depends on context, what you want to use. Okay, so let's do a hypothesis test. This one's wordy, I'm sorry. I cut out as much of it as I could. All right, so this one says the mean reading level of fourth graders in the state over the last 5 years was a Lexile reader measure of 850L. We don't even have to know about Lexile. Just measures their reading levels. Okay. Says the developers of a new program claim that their techniques will raise the mean reading level of fourth graders above the current value of 850L. Okay. They're saying they're going to improve the reading scores. The developers were given permission to implement their ideas in the classrooms. At the end of the pilot study, a simple random sample of 1,000 fourth graders had a mean reading level of 856. It is assumed that the population standard deviation is 98, using a 0.05 level of significance, should the findings of the study convince the education department of the validity of the developer's claim. So, first things first, we're going to do a hypothesis test. We need hypotheses. Okay. So, what claim are we testing here? We're testing these program developers' claim that they're going to raise the mean reading level of fourth graders. So we're dealing with means, and if we're going to raise it, and it says they're going to raise their reading levels above 850. Okay. So our alternative hypothesis, I'll call this step one. And our alternative hypothesis would be that the mean, that they're saying it's going to be above or greater than 850. That's the program developer's claim here that we're testing. Okay. And then we're going with the new additions way of doing the null hypothesis. We would just say the null hypothesis is that the mean equals 850. Okay. All right, so there are our hypotheses. Any questions on those? Getting those? Okay. Step two, we need to figure out which formula to use for our test statistic. Right now, that's really easy because we only have one. Okay, but let's talk about why we're using the one we're using. Okay. All right, so the parameter we're dealing with here is a mean. Okay. So we want to use one that deals with means. And also, we're given a number for the population standard deviation. So we're given sigma. Sigma is known here. Okay. So what I'm going to write down is we're dealing with means, and sigma is known. So that's going to tell us to use the normal distribution, to use a z test statistic. Okay. Our book also suggests to pick out the level of significance here. You can really do that anytime. By the time you get to the end, it doesn't matter. Okay, so we're just reading through the problem, looking for what level of significance we're using. So down toward the end, it says using a 0.05 level of significance. So I'm just going to make note of that. Okay, alpha on this one is 0.05. That's the number we'll compare our p-value to at the end. Step 3 is where we use our formula. Step 3, here's the formula again. That's the sigma, it's kind of skinny. That's still bad. Goodness. Right. Sigma. Okay. We need to pick out our numbers. Okay. Except for we already know what one should be. Mu, all we have to do is look at our hypotheses. Okay. So mu is going to be 850. Because mu is always the number that's in the null hypothesis. So we can go ahead and fill that one in. Okay. Then we can look back at the problem to get our other numbers. Okay, so we need a sample mean, population standard deviation, and sample size. Okay. So let's see. It says at the end of the pilot study, a simple random sample of 1,000 fourth graders. That's how many we had in our sample. That's N. Had a mean reading level of 856. The mean of our sample data, X bar. It says it's assumed the population standard deviation is 98, so that will be sigma. Okay. Then we just plug numbers into our formula. So 856 was our sample mean. Then we're going to divide by sigma, which was 98, over the square root of our sample size, which was 1,000. And if you're putting it in your calculator all at one time, you'll want to put parentheses around the top and around the bottom. Okay. Since it's a z-value, we'll round to 2 decimal places because that's all we can use with our tables. So let's see what we get there. 98 divided by square root of 1,000. So I got 1.9 and it rounds up to 4.94. Okay. So there's our test statistic. Step number 4, we want to draw our conclusion. So we need to come up with the p. We're going to use p-values. Okay. So we need to come up with the p-value of our test statistic so we can compare that to our significance level. So we've got the test statistic. The other information we need to come up with our p-value, we need to know is it left-tailed, right-tailed, or two-tailed. So we'll go back to our hypotheses. So here we have a greater than symbol. So what type of test? Right-tailed. Right-tailed. So for our p-value, we're going to want the area to the right of our test statistic. And so right-tailed. So we want area to the right of 1.94. So we can look up negative 1.94. We look up negative 1.94. I get 0.0262. And I usually like to write my p-value and my alpha down again beside each other. You always want to get in the habit of always writing them in the same order. Okay, so I always write my p-value first. So my p-value 0.0262. Alpha on this one, if I go back to step 2, right, alpha we noted was 0.05. So what's our relationship? We want to know, is our p-value smaller than alpha or not? So in this case, 0.0262 is smaller than 0.05, or in other words, our p-value is less than alpha, or if you prefer, our p-value is low. So what's our conclusion? What do we do with the null hypothesis? We reject the null hypothesis. If our p-value had been bigger than 0.05, we would fail to reject the null hypothesis. And if we want to interpret that, the claim we were testing the claim that the reading scores would increase, or were increased. And we started off assuming they were not increased, but we rejected that. So that means our data has overwhelming support in favor of the fact that the mean has gone up, so that the reading program did in fact work. So our conclusion there. Questions on any piece? It's our first hypothesis test, so if you got questions, that makes sense to have questions. Nothing you can think of? Not yet? Go on.
So like, let's say on the test, at the end of the problem, are you just looking at they reject it?
Most of the time, and in Hawks too, okay, most of the time it's step by step. So like you'll have a step that says state the hypotheses, and then I'll check that part. And then there'll be one that says state the level of significance. And then it'll be one that says find the value of the test statistic, one that says find the p-value, and then one that says what's the conclusion. Yeah. And when I'm grading, okay, so the issue here, if you mess the hypotheses up, you're in bad shape, okay, right, as far as getting everything else correct, okay, but so what I do when I'm grading is if you accidentally said mu was less than 850, okay, then what I do is I make sure you did everything correctly the way you thought the hypotheses were supposed to be. I'll count this part wrong, but if you do the other steps the way you should have, if that was the hypothesis, then you're okay. So it's not like the end of the world if you make an early mistake on these. Other questions? All right, let's do another one. Let's do another one. They get easier the more you do. And I left the textbook's explanation of stuff in here if you want to look at it. Okay. Let's look at this. All right. Since a researcher claims that the mean age of women in California at the time of completing a master's degree is less than 26.5 years, surveying a simple random sample of 213 women in California who have completed a master's degree, the researcher found a mean age of 26 years. Assuming that the population standard deviation is 2.3 years and using a 99% level of confidence, determine if there is sufficient evidence to support the researcher's claim. So what's our researcher claiming here? Our researcher is claiming that the mean age for women completing a master's degree is less than 26.5 years old. Okay, so our alternative hypothesis, I think the thing that gets us started, It'd be that the mean is less than 26.5. And for our null hypothesis, we use that mu equals 26.5. All right, so most important step out of the way. It's not too bad. Step 2, we need to figure out which distribution to use for our test statistic. Again, we only have one choice at the moment, so not too complicated, but here's our reasoning. Again, we're dealing with means, and we are given the population standard deviation, so sigma is known. So we're going to use z. Okay, we're going to use the normal distribution. So same reasoning as last time. We're dealing with a mean, and sigma is known. So use z. And also, we want to figure out the level of significance we're using here. This one throws us a little bit of a curve. It's not bad, but it doesn't straight up tell us what significance level we're using. Instead, it gives us a level of confidence. We just need to remember confidence is the area in the middle of our curve. Significance is the area left over in the tail or tails. Okay. So a little formula, and we got 99% confidence, C is 0.99. And so we got a little formula if we want alpha, 1 minus the confidence. So that's 1 minus 0.99. So here our alpha would be 0.01. They're just complements of each other. Okay. To 3, we can calculate our test statistic. So here's our formula. Okay. Mu we can already write down because it comes from our hypotheses. So for mu, we're going to use 26.5. Then we will go to our problem statement to get the rest of the information. Okay. So let's read about our sample data. It says surveying a simple random sample of 213 women, so that's our sample size, N. The researcher found a mean age of 26.0 years, so that's our sample mean, X bar. And assume that the population standard deviation is 2.3 years, so that's our population standard deviation, sigma. Okay. And we can plug those into our formula. Okay. So 26 or 26.0 for X bar. Population standard deviation was 2.3. We'll divide that by the square root of 213. That was our sample size. See what we get for a test statistic. Okay. This one I get 3.17. That's how that reads. Okay, so just real quick, the way that one I did the top part in my head, but what I would do is I would do 26.0 minus 26.5 in parentheses divided by parentheses 2.3 divided by square root of 213 close parenthesis, and then hit equal. You should get the number that way. We get 3.17. 3.17. So the only thing we're missing, we need some way to make our conclusion. I need to come up with a p-value. Let's see, I'll do that a different color. Maybe. Maybe I won't. Okay. So for our p-value, and our test statistics 3.17, well, we need to know which direction we care about the area. So we'll go back to our alternative hypothesis. Okay, so our alternative hypothesis here, we have a less than symbol. So what type of test is this one? The left-tailed, yeah, left-tailed. Points to the left, so left-tailed. On this one for our p-value, we want the area to the left. Oh, hang on, sorry. What did I mess up on step 3? Yeah, it's negative 3.17. I lost my negative sign in there. So we want the area to the left of negative 3.17. Sorry about that. So look up negative 3.17. There's a tiny little number there. 0.0008. Then I'm going to compare that p-value to my significance level. We figured out was 0.01. So this tiny little p-value is smaller than 0.01. Or in other words, our p-value is less than 0.01. So what's my conclusion? Do we reject the null hypothesis or fail to reject? No, p-value is low, so we reject. Yeah. Reject the null hypothesis. Yeah, it's an easy little rule, but it's hard to remember which one's which. Sometimes us on that little saying helps. You've been doing it forever like I have, it's second nature, but when you're learning, it's hard to remember which one's which. All right, questions on that one? All right, I've got one more for us, okay, because we've got 3 types, so let's do one of all 3 types. Okay. But a lot of the process is going to be the same, right? You kind of get in the routine. Okay. So get one more here. Okay, last one. And once you have one of all 3 of these, nothing different is going to happen in this section. Okay? The only thing that changes, right, your numbers change around, but the process is exactly the same. And it's always going to be one of 3 paths, right? Either it's left-tailed, right-tailed, or two-tailed. Those are only 3 options, so you're just filling in different numbers. Okay? All right, so let's look at this one. This is a recent study showed that the mean number of children born to women in Europe is 1.5. A global watch group claims that German women have a mean fertility rate that is different from the mean for all of Europe. To test its claim, the group surveyed a simple random sample of 128 German women, found out that they had a mean fertility rate of 1.4 children. Population standard deviation is assumed to be 0.8. Is there sufficient evidence to support the claim made by the global watch group at the 90% level of confidence? So first things first, we need our hypotheses. So what claim are we testing? We're testing the claim by the watch group that claims that the mean fertility rate for German women is what? It's different than the fertility rate for all of Europe. It doesn't say more, it doesn't say less. So we have to include both of those possibilities. So what symbol are we going to have? Not equal to, yeah. So we're going to test that our mean is not equal to the mean for Europe, which is 1.5. So alternative hypothesis, we're saying the mean for German women is not the same as for all of Europe, which was 1.5. Okay. So our null hypothesis that the mean does equal 1.5. Okay. Step 2, same as the others. Okay, we're dealing with means. We know sigma. So we're going to use z. And we want our significance level, alpha. Again, this one's giving us confidence instead, way down at the bottom. It says we want a 90% level of confidence. So we do 1 minus 0.90 to get significance. So 1 minus 0.9 or 0.90, 0.1 or 0.10, either way you want to write it. Okay. Step 3, to calculate our test statistic, it works just like the other two. So I'm going to write my formula down. Just so we can see what we're plugging in. Okay. I'm already going to fill in my number for mu because it's the number that comes from the hypotheses, 1.5. One thing that does for us to help us out is that when we start looking for our other numbers in the problem, when we come across 1.5, we know not to use it again. We've already got it covered. So we want a sample mean, population standard deviation, and sample size. Looking at our problem, we'll skip down to where it talks about the sample data. Okay, it says the group surveyed a simple random sample of 128 German women. That's our sample size, N. Found that they had a mean fertility rate of 1.4. That's the mean of our sample data, X bar. And it tells us the population standard deviation is assumed to be 0.8, so that is sigma. Just broke the tip on my pen up here. We'll make it, okay? Sigma. So we'll plug into our formula. So 1.4 over 0.8 divided by the square root of 128. What we get there. I get negative 1.41 when we round. For our p-value, this is two-tailed, so we got to keep track of two pieces on our curve. Right? So we got two z's we're concerned with, negative 1.41 and positive 1.41. We want the area in both of those tails. Okay, so let me take note of that it's two-tailed. Two-tailed. So remember our shortcut, we go to the one on the left, the negative one. We can look that up in the table and multiply that area by 2, okay, because it's two-tailed. So our p-value, we're going to have 2 times the area to the left of the z-value that's on the left, which is negative 1.41. So if we look up negative 1.41, get 0.0793. So my p-value on this hypothesis test is 0.1586. So if we compare 0.1586 to our significance level, which was 0.1, on this one, 0.1586 is bigger than alpha. So our p-value is not low. It's not smaller than alpha. So what's our conclusion? Yeah, we failed to reject the null hypothesis. And remember, that's a weak statement. Does that mean that our researcher is wrong here? No. All we can say is that there's not strong enough evidence in our data that we have to support the alternative hypothesis. If they go out and collect some more data, it may change. Yeah. It may not. I mean, it's a really weak statement on this one. Questions on those? All right, so good news is that 10.3 and 10.4 are really similar. We just have some tweaks to make, okay? But the big picture is going to be the same. The big picture is going to be the same on those sections. Okay? All right, if you didn't get it on our sign-up piece of paper that we have today, because I forgot the sign-in sheet, then make sure you get on there before you leave. And I'll see you next week. Have a good weekend. If you need some candy for the road, grab a piece.